Log on, tune in, find out. Another good idea from Cambridge.
Pleasure to have the series of lectures given by Clément Mouhot, who's now reader at the Center of Mathematical Analysis.
DPMMS. Huh? At DPMMS, that's the name.
At the Pure Mathematics Department here in
Yes.
Pure Mathematics.
Okay. So, thank you very much for this invitation, Jose, to give this series of lecture. I don't know if it will be pure math. It will be a mixed, I guess. So, during these 8 lectures, I would like to make an introduction, present the models, and many more physical debates that in the talks we have given, me and Cedric, in the last year. And this is based on several things. This is based on my own notes of the course I gave last year in Paris at IHP. Also the notes of Cedric, who gave 2 courses this summer. These notes are available on his website. And mostly, of course, it is based on the paper itself, which is even longer than all these notes gathered. Okay, so maybe first I will give you the summary of what I would like to do. So I would like to start, is it big enough? Yeah, okay. I would like to start with some introduction. Basically, the starting point and a bit of discussion of what I understand modestly of Boltzmann idea of irreversibility. This part for 5 minutes will be a bit philosophical, but to me it's interesting because then I will enter into the math and I would like to compare what we have proved to what I understand of Boltzmann idea of irreversibility. Then I would like to speak about what is mean field approximation, how you get the Vlasov equation from a particle system. And then we really enter, first, then a bit of, let's say, discussion about the Vlasov equation, Vlasov-Poisson equation, some mathematical discussion of this equation, Cauchy theory and so on, so forth. And then we will enter really into the details of the proof, first by looking at the linearized case. So linearized Vlasov-Poisson equation and linearized Landau damping. Okay, that's and then 4 we'll look at the nonlinear version, which will divide into several things, but maybe for today it's good to know. This is basically what I would like to do for the next this week and the next week, if I can. Okay, so the starting point. Yeah, and feel free to interrupt me. That's the goal of this kind of lecture. So starting point is the following, in a few words. 2 papers, Landau. So I've made at least 2 breakthroughs, but in plasma physics, has written 2 very famous papers. The first one, in 36, is a paper where Landau derived the so-called Landau, let's call it with the word of today, Landau-Coulomb equation, which is what? Which is a modification of Boltzmann equation for plasma. Okay, and importantly, in terms of new concepts, Landau introduced the idea of a relaxation like for the Boltzmann equation in plasma physics. What I mean like Boltzmann equation, I mean with entropy increase and loss of information, which is more or less the two different ways to say the same. So this equation I will not study in this course. This is a modification. This is a collisional kinetic equation. And 10 years later, so in between these two papers, in the team, I think it's the same team, in the same team of Landau, Vlasov in 38 proposed a non-collisional kinetic equation for plasma with mean field term. That's what we will look in the first part. And in 46, Landau proposed something totally different. He proposed some relaxation phenomena with constant entropy. Which is based on the non-collisional Vlasov-Poisson equation, so derived by Vlasov. So non-collisional, and the computation of Landau, which will be, I will not show you exactly the computation that it was done historically, but we will basically prove exactly what Landau proved in one of the first part of the course. And so it is, the equation does not take into account collision. So you say plasma interact by mean field. It's a reversible equation. Mathematically, it's an Hamiltonian PDE. And Landau was proposing on a linearized, through a linearized computation, some relaxation phenomena, and which I will explain more in detail. At the time, he was calling this damping of the spatial waves. And in particular, the electric field was damped, which is the thing you will, if you're a physicist, which I'm not, you really want to measure in a plasma. Okay, so that's it for the, let's say, the starting point. Maybe let's not do the computation right now. So this has triggered an enormous amount of paper on how to interpret this. You have an Hamiltonian PDE. Here is the situation. This is a kinetic PDE. We will write it in a second. So the unknown function is a function over the phase space of position and velocity. And Landau says, well, the observable, the velocity average, are converging to something asymptotically. There is something like relaxation to an equilibrium. And so this idea looks very strange, and which also has increased the number of debates, is that Landau computation is based on a linearized Vlasov-Poisson. And it is not clear at all if you can deduce something on an Hamiltonian PD from its linearized version asymptotically. I mean, it's wrong in general. Okay, so just a few words about irreversibility and entropy. So let's say according to Boltzmann, so this is based a lot on the discussion and reading and discussion with and reading of papers of Leibowitz in Physical Today, for instance. So Boltzmann, so these are PDEs, let's say, to describe an infinite number of particles. Boltzmann, at the time, the starting point was a careful reading of Maxwell paper of 1867, Maxwell. Well, let's not go into details, but Maxwell derived the so-called Maxwell distribution at equilibrium in velocity, plus a weak form of what is known now as the Boltzmann equation. And then Boltzmann asked about relaxation to this distribution. So long time behavior. So the exact quote, he started the paper saying, well, Maxwell has not proved that you converge indeed to this distribution, and that is the goal he has in this paper. And so he derived Let's write it now, which you all know very well. In his paper, he writes the Boltzmann equation in a strong form, which was more or less already written in the paper of Maxwell, but this is not all. He's very famous, and his name is associated to this equation because he also noticed that you have some functional, not only noticed, but he explained why, according to him, why you have a functional which decays, the H functional, which is the opposite of an entropy. So this equation is irreversible. And so the idea to explain these kind of things, of course, you need to think a bit, because Boltzmann equation, like Vlasov equation, is supposed to be obtained from particle system. Here you have the Newton equation. I will write more in a second. So it's reversible. And then you want to pass to the limit in some way. And you obtain the Boltzmann equation, which is irreversible. So this discovery of Boltzmann had many consequences in physics, of course, and also in maths, because more or less it brought the second principle of thermodynamics into the field of analysis. We could start to work on it and to try to prove it and so on. But also you have to explain this, and then Boltzmann had another to me extremely influential idea. Oh, I wrote it in French. Anyway, you have to revert the two words. The molecular chaos assumption. So how is it possible to go from reversible and irreversible? And this, I just want to make you a short picture, which you have to keep in mind when we give you the statement about Landau damping. It goes like this. This is a microscopic dynamics, where you have all the particles. This is, let's say, macroscopic, even if you could argue that Boltzmann is mesoscopic, but let's don't care. This is much larger description than this one. Then assume you have on the left the evolution at micro level, on the right the evolution at macro level. So on the left it's Hamiltonian dynamics. You have a full group. Okay, working in some abstract phase space, let's call it W. On the right you have a semi-group, let's call it FT. And I don't want to specify where it lives, but let's say we start from some macroscopic state M0. Okay, this macroscopic state corresponds to some possible microstates here, okay, associated with it. This is at time 0. And you have something, I don't know, let's call it W naught, the part of the phase space associated. Then you look the evolution. Still your phase space. And this evolves towards something new, M1, a new macrostate, which corresponds to something. If, so this is my way of interpreting, of course this is my intuition of it, if you can factorize these dynamics, so factorizing means something precise here. By factorizing I mean you want to write something like, okay, this M0, I take the notation is M of M0. Just to recall, this is the pre-image of this guy. If X belongs to the microstates associated with some guy here, then at later time, it will be a microstate of the good macrostate along the good evolution. Is it clear what I mean? Okay, I mean here you have an evolution, and a closed evolution for a mathematician means we want to have a closed PDE here to study the evolution of this macrostate. And this is highly non-trivial to have this. You could imagine, let me show you a bad situation, you could imagine that, for instance, here a part of it break into another microstate. Of course, if you have this, you cannot have a closed equation at the macro level. So at the same time, this factorization assumption is extremely non-trivial, and I have to say it's mostly open at now. The only result I know which proved this kind of thing is this small time result from Landau. And at the same time, it is extremely natural from physical point of view, because it's the minimal things to say if you want to have a closed law of physics at a macro level. You need to say something like this. So you assume you don't have this, and let me stop with this kind of physical debate by just saying something. Then Boltzmann introduced a very deep notion of molecular chaos. He says something like, well, for some very particular initial data in the phase space, there will be a property, molecular chaos, which means more or less no extreme decorrelation, which will be propagated as time goes on by this Hamiltonian flow. And for this very peculiar initial data, then you can close a law at the macro level associated. So let's write it in different way. Very rare, uncommon, initial data. Another way to say is very decorrelated. Still another way to say is very low entropy initial data. Because something I have not written on my picture is also what is extremely famous about Boltzmann, is that if you have this picture in mind, then you can understand what is the notion of entropy of Boltzmann. He defined the entropy of a macrostate as, up to a constant k, the logarithm of the volume in phase space of the microstate associated to the macrostate. So this is the idea of entropy of Boltzmann, and it's extremely beautiful. Why? Because look, if you assume that this factorization holds, first it can only increase. Well, yeah, it depends. Sorry, yeah, the H function of Boltzmann will be plus. Yeah, sure. Yeah, sure. I was still using the H function convention. Yes, sure. And so you see that this volume will only increase if the factorization is correct, because only new guys can join you. You never split, more or less, if you continue the evolution. But it can increase. It can increase strictly. You can perfectly imagine that some other microstate will finally have the same macrostate, and that's what happened in a box with two gases. I mean, the very famous experience when you remove some barrier in the middle of the two gases, then they go towards the same macrostate. So you really see why there is something that should grow. And from this idea of Boltzmann, you see that irreversibility at macro level is not contradictory with this. It's a consequence of this. It's a consequence of the fact that you look a microscopic dynamic through some selective glasses, if you want. You just average, you look some observables of a system with many hidden variables, and the fact that you can close an equation at the macro level. Okay, so very rare initial data, decorrelated, low entropy, will produce something irreversible at this level. And this is quantified by the entropy functional, which will increase for the macroscopic behavior. So the key idea I want to keep in mind is this. Irreversible, you start from a reversible Hamiltonian dynamics. You do something like, call it how you want, projecting, averaging, meaning that there is less information at this level than here. And you can see something irreversible at this level for some initial data carefully chosen. In the Landau damping, this will be the full equation. This will be the density of the electric field. And we have a very small neighborhood of initial data which produce this irreversibility. But what we miss, we cannot close the factorization, and we have nothing looking like an entropy for the electric field. I mean, we don't know how to do this, at least. Okay, so now I will go into the mean field approximation. Okay. So, yeah, maybe things I have not said. Well, the idea of Landau have also had many consequences, but we'll talk again later on, like violent relaxation concepts. And many people here in Cambridge have been associated with these progresses, like Lyndon Bell, that we will talk again in a while. Okay, so what is mean field approximation? Is a way to derive the so-called mean field kinetic equation, which are modeling long-range interaction. So I don't want to go into the subtlety of when are you long or short range. Let me just give some examples. Typically, this is used for describing interaction in a plasma by Coulomb force. And interaction by Newton force, gravitational force, in a gas of stars. That is a galactic dynamic. Okay, so then this will be the Vlasov-Poisson equation. The other big class are the collisional models. Most important one being the Boltzmann equation, which are describing short range interaction, or at least shorter than this. And of course, you could perfectly imagine to mix these two viewpoints and so on. And so far, these models are reversible, these models are irreversible. So let's start with the Newton equation at the level of particles. So we start with the fundamental principle of dynamics. For the position of a set of n particles, okay, so what it means, I between 1 and n. You look at the equation for each particles with a force exerted by the particle j over the particle I, and you sum over j. So I won't speak about relativistic and so on, quantum, just at the classical level, classical dynamics. Then you could imagine to change to have very different masses, like it's used to traditionally done when you look the solar system. It's very important in applying CAM theory, for instance, saying that the sun has a bigger mass and so on. Here I will take the same mass for all particles. So I will go to adimensional unit as soon as possible. And the force, second assumption, I will take the force in gradient form, deriving from a potential, okay, depending on the distance, the relative position between the particles. Okay. So typical example, of course. First one is rho prime. So this is the interaction between two bodies with mass rho prime. You put some positive constant, you divide by the distance. In dimension 3, this is the gravitation force. Okay, in my convention, let's put a minus here for the gravitation. And for the electric, yeah, for the, well, okay, let's call this mm prime, not to confuse with the next one. And in the case of electric force, let's call the charges rho and rho prime with a plus. Okay, so this is the main model for attractive force and the main model for repulsive force. But then, since we are doing math, you could perfectly imagine to have more general W. And in fact, well, let's say as meta principle, you can always more or less always find some physics situation where there will be the W that you use in your mass models. So, of course, then what happens? What happens is that this dynamics is intractable for many reasons. It's intractable first, not only because n will be large, it's also intractable because as soon as n is greater than 3, you have even problems to analyze it at a theoretical level, the three-body problem and so on. So you have a level theoretical, let's say dynamical problem, and moreover, typically n will be enormous. So n, this is the number of stars in the Milky Way. This maybe should be the number, the number of particles in the plasma in the solar kernel. So just to give you idea, so this is absolutely huge. But then what will happen is that for 2 particles it's okay. For 3 with similar mass there are problems and more. But then for infinite number of particles we can do something. So this is the mean field limit itself. So this, we will follow a very general principle in mathematical derivation. We have something which is with, let's say, large number of dimension, which is linear. A linear dynamics on a space with enormous dimension. We will go through a derivation process to a single particle evolution at a nonlinear level. So you trade one difficulty for another, more or less, but still, clearly we know much more things at this level than the many particle system. Well, okay, I will skip this part. So, main difficulty is a difficulty in doing this. What can you do when the dimension of your space goes to infinity? Okay, you typically imagine that, let's write, I don't know, one particle belongs to something, let's say, E. I don't want to care so much. This can be RD, this can be a bounded domain with some boundary conditions and so on. So this is the domain. Then my whole system here belongs to En. But in fact, if I go to a first order differential equation and use the velocity also, then I will write a system even worse. In E to N. So the difficulty in this is first to find some, let's say, fixed ground on which proceeding to the limit. So another thing to say, that's the main difficulty. Another thing to say is that we have to take into account that the particles are indistinguishable. That's let's say that's very important, that the microscopic counterpart of one of the basic ideas found in kinetic theory, which is that you're searching for the evolution of distribution of particles, and you don't care about what each particle precisely is doing. So at the micro level, we assume this indistinguishability. And then here is the way of plunging the many-dimensional dynamics into a fixed space. So what I'm describing right now is the most common way to proceed to a mean field limit. Also, it's not the only one, and it's also the oldest one. So there is a one-to-one correspondence between what? Between some particles after taking some quotient. I don't want to write this because it's not so interesting at now. You take the quotient by permutation. Okay, I say a set of particles is the same as another one, see if you can obtain one from the other by permutation. And then you associate the empirical measure. And let's call it as it is used to do, like this. Just like this, let's say. Okay, mu hat n. So now this lives in probability of a one particle space. And this is equivalent. You can go back. The indistinguishability is included in the fact that you cannot distinguish between the Dirac masses. Okay, and so now we will use this mapping to express an equation over this guy, to write an equation over this guy. Let me give a statement. Assume some minimal regularity. I mean, it is not the minimal one, let's say. Assume some good regularity on the interaction potential. So you remember this is the potential producing the force field. And for this I've already introduced the notation. Then the two statements of equivalent, two following equation equivalent. So either I write the Newton equation for any I. So forget about the mass. I normalize everything. I want to keep track of some coefficients here for the force because I will scale it later on. Okay, so these are still the Newton equation. And I can write it as a PDE in weak sense, meaning weak because I'm looking at measures, solution. Like this, where, let me tell you, okay, so you have these two equations, and let me tell you how you compute f here, fn. And you compute fn as a convolution with the empirical measure let me just say, emphasize that this is exactly the same as saying this. At point x, this means this. Okay, and here the xj are precisely the position of your particles. Convolution in V, this is purely decorative. You can remove it because this does not, this guy does not depend on V, so just integrate over V. And then you have a convolution in X, but you convolute with a Dirac mass. So it means you take the function at point xj. Okay, so this is really your force. So these two things are equivalent, and I just want to warn you that this is not the same as writing the Liouville equation on En associated with this. The Liouville equation on En associated with this is linear, and this is nonlinear. But this is an equation on a fixed space for the probability for a single particle. Second point, so this solves the difficulty of getting to a common ground. And second point, assume that the gradient of the interaction potential is uniformly continuous. Then, and the fact that the initial data is such that if you take the empirical measure associated with the initial data, let's call it 0, it does converge to something. Let's call this mu naught in weak sense. Okay, and then for later time, and then you have a scaling assumption. I will comment on all of this. You assume that your C was indeed depending on n. So let's write C of n. Okay, and you assume that C of n times n goes to a constant. Then under this assumption, for n going to infinity, and at later time, your empirical measure weakly converge up to extraction to some mu t, which solves okay, I'm writing it here, dt of mu plus v grad x of mu plus s of t x grad v mu. Okay, and here the force is computed again as minus grade w convoluted with mu. Okay, so let's stop and comment a bit. Yes.
The constant C itself depends on n.
Yes, I will. Let me explain why. This scaling is exactly what we call the mean field scaling. So mean field scaling, and this is very different from something I won't speak about, which is the Boltzmann-Grad scaling. The mean field scaling means everybody in your population interacts over everybody with a scale 1 over n, like O of 1 over n. Okay, so everybody feels the influence of everybody, but if you take one guy over another guy, it's very small when n is big. But if everybody interacts over everybody with 1 over n, if you are one particle and you look at the influence of all the other one, then it will be of order 1. Okay, so you feel the collective influence of all the other particles, but you cannot see the influence of a particular particle. This is exactly the idea of mean field. So this is a scaling. Another thing important in this scaling is that it's a scaling where you feel the influence of everybody in the population. In a Boltzmann-Grad scaling, you feel the influence only at the same position. It's a localized scaling, if you want. And so this is extremely important. This is required. You ask more or less that you have something like a law of large number at initial time. This is looking like a law of large number. because if you pick this randomly with this law, you can prove that this holds, more or less, these kind of things. You can reframe it as a chaoticity assumption. I won't speak about this, but the notion of chaos introduced by Kax is equivalent to such a statement. And you prove that at later time this holds, which means you propagate the chaos in Kax's world. And so your empirical measures do converge to something, and then it solves the Vlasov equation with force F. Okay, and if you plug the Coulomb force or the Newton force here, this is what we call the Vlasov-Poisson equation. So let's do some remarks. So you have to understand the equation here in the sense of distribution. Well, I mean in weak sense, in dual form. There is no problem. Well, if you're used to this, you know that you should not multiply to distribution and so on, but here your force is a convolution with something nice, so you don't have any problem. Well, the expression of the force, let's give this expression a more usual form. It means that the force is given by the convolution with W, with great W, of the velocity average of the solution mu. Okay. So by weak sense, I mean, for instance, narrow. But here, since we are handling only probability, all the weak senses will be equivalent because all the masses are 1. Okay, so maybe a sketch here. So assume that well-posedness is okay. And let's test the second equation I gave to you. Okay, let's test this equation against the test function. So what you obtain is the following. Okay. Then don't forget that in this equation, mu hat n is produced by computing the empirical measure along the trajectories of the Newton equation. This has to be used sometime, somewhere. Okay, so then we use the chain rule. So it expands in 2. So you do the chain rules and you use what means Okay, first let's do chain rule. VI. Okay, I just expand what is here. Okay, the first thing here gives me these two terms. Second one, I just plug xi vi into here. Okay, here everywhere it is implicit that phi is taken xi vi. So then you can simplify these two guys using the Newton equation. Xi dot is vi, and then you end up with the following. And this should hold for any test function phi. Well, in something nice, infinity compact support, and so on. Okay, and then if you take phi correctly, so I will cheat a bit. So supposing that your particles are all at different points at the moment, you can build a test function which is, let's say, localized around one particle and 0 on the other. Okay, assume you can do this. Then it implies, by choosing carefully phi, that for any I, vi dot is Fn of t of xi, which is precisely the Newton equation. Okay, if it's still written somewhere. Okay, you see Fn is the sum of the action of all the other particles on this one. Okay, the last blackboard on the right. And you can make this rigorous by saying that all the implications are in fact equivalent here. Okay, so now let's do the limit. I'm just sketching. So let's say you work on a finite time interval. You will prove some tightness, compactness of your sequence of empirical measures. So I just give the main ingredients. Then if you have something like this, then it's a very simple exercise to check that Fn will converge to some force F, which is given still on the last blackboard, this F here. Okay, because your W is smooth. If your distribution converges weakly, then the force will converge strongly, because you convolute it with something nice. Since you have a lot of regularity here, still check that this is able to, you're able to prove this in the sense of distribution. Okay, because you will be multiplying a measure by something smooth, and then pass to the limit simply in this equation. I just give you some ingredients for this guy because these other guys are linear. Okay, so as soon as you have a weak convergence in measure, it's a convergence for distribution, and so you pass to the limit from this equation to this one. So that's about the, even if you need to detail, but it's straightforward computation, that's about the full idea of how you can derive Vlasov equation. So before stopping on this, let me just make a few remarks. Yeah, just give a few remarks and stop. So first, so I won't make the state of the art, but first notice that there is a lot of smoothness on W here, okay, which is not available for the main physical interaction Coulomb and Newton. And actually doing all this process is a huge open problem. To make all this process rigorous is a huge open problem. So when I speak of these two interactions, so remember you take this equation with really W scaling like 1 over the distance, plus or minus depending attractive repulsive. This is the Vlasov-Poisson equation. And this is still a major problem to derive correctly the Vlasov-Poisson equation from a particle system. Second thing is that still with smoothness you have much more quantitative result. This is based on compactness argument, but you have much better thing. For instance, by Dubroshin, if you show stability, I won't detail here, but this is a very simple but extremely nice idea. If you show stability in Wasserstein, it means you show stability at a measure level for the limit equation. Then, in fact, the miracle which is at the basis of all this computation here is that if you plug the empirical measure here, you go back to my Newton equations equivalent to the nonlinear PD on the empirical measures. So if you're able to prove a quantitative stability with a distance over measures, and the Wasserstein distance exactly provides this, then you can quantify this mean field limit. If you want to be more pedantic, you can say that you propagate a rate in the law of large number in this measure. Okay, there are many other works. Maybe last, and the last thing I want to say is a bit more conceptual in a way. What is the difference between this equation and, yes, it's still here. I mean, after all, these are exactly they have exactly the same structure. To me, at least, that's a natural question. What makes a difference between calling this a Vlasov-Poisson equation and calling this the whole dynamics of the Newton equation? What is different, in fact? So the difference is a continuum smoothness. By this I mean is that if you study this equation in measure space, allowing for Dirac masses, this contains fully the dynamics of the Newton equation. And if you study this equation in L1, then you enter the world of PDE. And then it's a mean field dynamic. So what I mean is that the translation of this physical idea of a particle dynamics and a PD dynamics for this limit, you see the difference really at the level of in which space you study the limit equation. If you study the limit equation in probability space, then it is again including all the Newton dynamics. Yes. Okay, maybe let's do the break now.
We resume in 25 minutes or so, and we postpone all questions to the break. And